Before we take a look at the other schemes of feedback, namely integral control, derivative control, and even more general types of feedback control, we should look at the transient response or the transient behavior of our speed control system. Why? Because, as I said earlier, in the feedback scheme that we had talked about, namely proportional control, it looked as if you could reduce the steady state error when disturbances take place to any arbitrarily small amount by increasing the gain Ka sufficiently. So there does not seem to be any problem. Nowadays, of course, high gain amplifiers are readily available, so that's not a big problem. So why not just have a very large gain Ka so that the steady state error because of disturbances will be reduced considerably. The reason for not increasing Ka to a very large value is because of problems that occur in the transient behavior of the system. And so this is something that we should take a look at before proceeding further. And there is another reason: when you introduce other kinds of feedback, the transient behavior is going to be different, and who knows, the transient behavior may be worse than what it is with proportional feedback. So transient analysis or analysis of the transient behavior of control systems is an absolutely a must. And you have already studied to some extent methods for finding out the transient behavior, or in fact the behavior of a system as it progresses in time. Sometimes there is a steady state, sometimes there is no steady state, the input may be periodic, and so on and so forth. So we will take a quick review of some methods of finding out the behavior of a system. For this purpose, then we have to go back to a description of the system that applies not in the steady state only, but applies at any time. That is, applies irrespective of whether the signals associated with the system, the variables associated with the system, remain constant or not. So this means that some things which we had ignored earlier cannot be ignored any longer. And what is it that we ignored earlier when we looked at our motor problem? Because of steady state considerations, that is because we said that, all right, the torque will be constant, the applied voltage will be constant. So after some time, the armature current will be constant, the motor speed will be constant. And because of this, we made some simplifications, or we simply ignored or deleted some terms in the equations. These terms were arising out of some kind of inertia of the system. In the electrical part of the system, that is the armature circuit, we ignored the effect of armature inductance or any inductive effects in that circuit. Specifically, we ignored the effect of the armature inductance La, or to put it differently, we put it equal to 0. Of course, we could have similarly ignored the armature resistance, but if you ignore too much, then what you will get will be such a poor approximation to the actual behavior that it will be of no use. And now that we are going to look at transient behavior, that is when the signals and the variables are no longer constant but might change, either because of disturbances changing continuously or because you have not really reached the steady state yet. The motor has been switched on, but it has not reached its final speed, and so the speed is increasing. So La cannot be ignored because the armature current may not be constant. The armature current, starting from the moment the motor is switched on, will finally go towards its steady state value, but during this time it will be changing. So we have to take account of LA. And in what way? In the equation that we wrote for the armature circuit, we had armature voltage equal to the back EMF, of course, that remains as it was, KB into omega m, plus the armature resistance drop, that remains as it is. In fact, we called it the armature drop, but now we have one more term associated with the armature, and that will be the inductance drop. So modeled by as LA into DIA dt. How to measure this armature inductance, etc., this is something I am not going to discuss. In machines courses, one does talk about these inductances and other parameters associated with a machine. And in fact, with an AC machine, the situation is even more complicated. Let's assume that somehow this LA has been found out, so many henries or millihenries. So now we cannot ignore this term LA DIA dt, because IA is not constant, so DIA dt is not 0. So this term LA DIA dt is not 0, and it may not be very small either. It may be comparable with the armature resistance drop, or it may be even larger than that. So we are not going to be able to ignore it. As a result, now our equation is no longer an algebraic equation, and that too it was a very simple linear algebraic equation in which the variables EA, omega m and IA were simply multiplied by some constants. It is no longer an algebraic equation, but it is still a linear equation, only it is now a linear differential equation. Linear differential equation. That is an equation in which derivatives of the variables also appear in addition to the variables themselves. So in this equation we have not only IA, but also its derivative DIA dt, the rate of change of armature current, appearing in the equation. Of course, we have omega m, the speed, instantaneous speed, and the applied voltage also appearing in the equation. The equation is linear. At this moment, I would just like you to think about this word linear and be ready to answer the question, why is this equation said to be a linear equation? There is a simple answer to that, simple in the sense an answer which is good enough for some purposes, but not a general enough answer. And there is a more advanced or a sophisticated answer as to why this equation is a linear equation. It is a differential equation because there is a derivative appearing in that equation. This is as far as the armature circuit is concerned. Therefore, we no longer have a simple linear algebraic equation, but we have a linear differential equation. Something similar is happening in the mechanical part of the system. We had ignored the moment of inertia of the motor and load combined, J. This, like the inductance, plays a role when the speed of the motor is changing or there is angular acceleration of the motor or the shaft. And so its derivative, the derivative of the speed, will appear in the equation, and the equation is no longer what it was earlier, but it will be now motor torque equal to the torque constant into the armature current, that remains as it is. But now this is made up of three parts. One is the load torque, as before. The second term is the torque required to overcome friction, that also remains as before, kf into omega m. But now I have a third term, which is the moment of inertia multiplied by the rate of change of the speed or the angular acceleration of the motor, j d omega m dt. Earlier we had only two terms, the d omega m dt term was not there, but once again, if omega m is not constant, that is, we are not considering steady state, then d omega m by dt may not be small, and even if it is small, this product j d omega m dt may not be small, because the moment of inertia can be quite large. And so this term cannot be ignored in comparison with the frictional term or even in comparison with the load torque, and so we have to look at that term also. And as a result, our equation is no longer an algebraic equation which it was earlier. It was a linear algebraic equation involving the three variables or functions: armature current, motor speed, and load torque, multiplied by coefficients which were some numbers such as Kt and Kf, and load torque was simply multiplied by 1 if you want to think of it as multiplied by anything. We now have this additional derivative term, so we have a differential equation, and it is also a linear differential equation. So we have now the behavior of the motor and load when armature voltage is applied directly, described by two linear differential equations. In one of them the derivative of armature current occurs, and in the other the derivative of the motor speed occurs. There is something more that can be said about these equations. Not only are these equations linear, but the coefficients that multiply these variables, they are not functions of time, but they are numbers or constants such as Kb, Kt, Ra, La, Kf, J, and coefficients 1 multiplying the applied voltage and the load torque. So they are not only linear differential equations, they are linear differential equations with constant coefficients. We could abbreviate it by LDE, linear differential equations, W with constant coefficients, LDEWCC. And we have not one equation, but we have two equations. Now the problem that therefore one can consider is the following. The behavior of the motor is described by these two linear differential equations with constant coefficients. Suppose we apply some armature voltage and keep it constant. So that is a special case, of course. Later on when we think of feedback, the armature voltage that is applied is not going to be kept constant because it is produced by a generator, etc. But for now, let us consider the special case when the applied armature voltage is just a constant. It does not change with time, 230 volts. From the moment the motor is switched on, the applied voltage is kept at 230 volts. Similarly, we could say that the load torque is also kept constant, let us say 30 Newton meters or whatever it is. Or we could allow, because it is more realistic, for the load torque to change. So we may consider that the load torque TL will be a function of time, and we could consider various ways in which the load torque may change. So what then is required is to obtain from these two equations how the motor speed omega m will vary as a function of time. That is, what will be omega mt, the motor speed as a function of time. What is going to be omega mt if Ea is given a constant value and the load torque variation TL of t is given by some particular function. So TL of t is given, find out omega m of t. Ea also is given, find out the variation of the speed. Of course, as you know, because you have looked at some simpler differential equations in your mathematics courses as well as in your electric circuit or network theory courses, that in order to solve the equation, it is not enough to only know the inputs, in this case Ea and TL. TL of course is going to serve as the disturbance input, Ea is the other input, but we also need to know what are known as initial conditions, certain initial values of the variables. Of which variables? The variables whose derivatives appear in the equation. They are sometimes referred to as dynamic variables for this reason, that is, their derivatives appear, not just omega m as a function of time, but its derivative occurs in the equation, not just Ia, but its derivative occurs in the equation. So for such variables we need to know initial values. Now what do we mean by initial values? What we mean is we are going to look at the behavior of the system from some particular moment of time or instant of time onwards. what happens thereafter. Now, as you know, it is convenient to choose that moment of time, the starting moment of time, as the number 0, that is, we call it t equal to 0. Start your clock at that moment when perhaps you have switched on the motor. So that is what is meant by initial. Now, at that time, what will be the values of these dynamic variables Ia of t and omega m of t? Now, of course, if the motor has been at rest, if the power supply EA has not been switched on, then you do not expect that there will be some current flowing in the armature, because after all, what will cause flow of that current? So in this case, we expect that Ia, the armature current at time 0, will be 0. Similarly, I said that the motor is at rest, so omega m 0 is 0. So these will be the two initial values. The armature current is 0 at t equal to 0, the motor speed is 0 at t equal to 0. That is, the initial values of these dynamic variables, motor speed and armature current, are both 0. Now, this may not always be the case. For example, suppose the motor was running at certain speed with certain applied armature voltage EA and some load torque TL, and suppose at some moment of time you decided to change the applied voltage, or the load torque was changed at that moment of time. The motor was in the steady state, the motor was running at a constant speed with a constant applied voltage, with a constant torque, load torque, etc. Constant speed, constant armature current, everything was as if it was the steady state. But then suddenly or deliberately EA was changed or TL was changed. Now, in that case, we start our investigation from this moment when these changes are taking place. So we will say that that will be our t equal to 0. That will be our initial instant of time, and we will look at the behavior from there onwards or thereafter. And therefore, then the initial values will not be 0, because the motor was already running, the armature already had some current. So the armature current at that moment of time, of course, we may choose to call that moment of time 0 once again, because it is a new investigation. So then Ia 0 may not be 0, and of course the motor was running, so omega m 0 is also not 0. So the initial values may not be 0, they may both be non-zero. But as a special case, when the motor was at rest and the circuit was not connected electrically, the armature current and the motor speed were 0, and therefore the initial values will be 0. So the problem is, given a system or a set of differential equations, in this case linear differential equations with constant coefficients, given the specific input functions, the behavior of the variables EA and TL, maybe both of them are kept constant, or one of them EA is kept constant, TL is varied in a certain way, or both are changed in some specific ways. Knowing how EA and TL are going to change with time, knowing the initial values, obtain or calculate or find out omega m as a function of time and perhaps Ia also as a function of time. This is the problem of solving differential equations with initial conditions or with initial values. Now, there are many techniques for solving differential equations, especially equations which are linear with constant coefficients. So, for linear differential equations with constant coefficients, there are a number of special techniques available. Of course, in the last analysis, one can always use a computer program and a package of computer programs to solve a system of equations. Numerical analysis procedures and programs based on them, numerical analysis procedures like the Runge-Kutta technique or the Milne technique and so on, there are many that are available. They are numerical methods for obtaining an approximate solution of a differential equation, not necessarily linear, not necessarily with constant coefficients. But for the moment, we are only looking at a very simple problem. We have systems of equations which are linear with constant coefficients. So it is fortunately possible to do something about them and get some idea of what the solution will be like without submitting it to a computer program and then waiting for whatever comes out. As I said, the purpose of all this study is not just to compute some numbers, but to get some insight into what is possible, what is going on, and so forth. One applied mathematician said, by name Richard Hamming, said this very nicely: the purpose of computing is insight, not numbers. By that, what he meant, of course, was the purpose of computers is not only to get numbers, but to get some insight into what is going to happen or what is happening, and to consider alternatives and make changes and so on. The purpose of computing is not just to calculate or solve a particular problem and that's it. That is, of course, important, but many techniques have to be studied so that one can get some insight into what is possible, what is expected, and so on. So we will look at some of the techniques that are applicable for linear differential equations with constant coefficients, and this will be basically a review of what you have studied already in your mathematics course, and also perhaps in your course on networks or electrical circuits. One of the techniques which is used and which we will use, and control theory people have been using it for almost 60-70 years now, is based on the use of what is known as the Laplace transformation. So this is one technique, the technique of Laplace transformation, or the technique that uses or applies the Laplace transformation. This is a very popular technique with control theory people, so certainly we will look at it, and all of us should become familiar with this technique. Therefore, that means that we must know a little bit about what this Laplace transformation is, and as a technique how it is used to solve or to help solve linear differential equations with constant coefficients. So this is one technique, the technique that uses the Laplace transformation. But there are techniques which are little simpler than that, and in fact some of those techniques probably you are already familiar with from your mathematics courses, especially when you have a single differential equation, but which may involve not only first order derivative but higher order derivatives of the unknown function. For such an equation, that technique is applicable. Of course, that technique has to be used with certain modifications and certain care and so on. Let me give an example. We can of course make a beginning with a simple equation. The simplest differential equation will contain what? It will contain linear differential equation with constant coefficient. Since it is a differential equation, a derivative must appear. So what is the simplest derivative of a function? It is the first derivative, or the derivative of the function itself. So suppose the unknown function or the system response or output function is x, then its derivative, and for us these are functions of time because we are interested in what happens as time passes. Our variables are functions of time. So x is x of t, really function of time. We have its derivative dx dt. In the equation the derivative must appear, and so a general first order, and that's why it's called a first order linear differential equation, because only the first order derivative occurs in it, will be something like dx dt plus, let's say, some coefficient, and I'll call it a0, and you will see why I am going to call it a0, plus a0x equal to a function on the right hand side which is regarded as an input. In mathematics one may use for it the symbol y, but in control theory practice for the input a general symbol that is used is u. For some reason, not u is not from English but it's from another language, namely German, that the letter u has been selected. So the input we call it u of t. Of course, in a particular case it may be armature voltage, it may be something else, it may be a force or what not, but it is a function of time which is the input. We have the response or the output x, but its derivative also appears in the equation, and I could have put a coefficient with the derivative, but that coefficient must not be 0, otherwise there is no point in writing the derivative. So if that coefficient was, let us say, a1, then I could divide the equation through by a1, and therefore I can imagine that dx dt has only coefficient 1. So I have this simple first order linear differential equation with a constant coefficient for only one function x. X is the output or the response function. It may be the response of a system to an input function, or sometimes one uses the word stimulus. This stimulus response comes from physiology and psychology. In control practice we use the words input and output. So u is the input, x is the output of the system, and the system behavior is described by this simple first order linear differential equation with constant coefficients. And now we want to solve this. One technique, of course, as I mentioned, is the Laplace transformation technique, but is there any simpler technique? You will recall that there was a simpler technique. In fact, that technique starts off with a differential equation which is even simpler, namely dx dt plus a0x equal to 0. The input has been put equal to 0. What is such a differential equation said to be? It is said to be a homogeneous differential equation, or we could call it in control theory language as a zero input differential equation, or we can say that the system is free. The system is not subject to any force or any external action. It is a homogeneous differential equation. When the right hand side is not 0 or the input term is present, then one talks about the system being forced. And this, of course, this is a term that comes from mechanics, that is the actual force applied to a mass spring system or a mass spring dashpot system, and that is why that appears as an input in the differential equation. So one uses the word force and you say that the system is forced. So a simpler case is when you have a homogeneous system or a free first order linear differential equation with constant coefficients. So we just have dx dt plus a0x equal to 0. Now what is the solution of this equation? Now of course everybody ought to know the solution of this equation, because the solution of this equation is what is called the exponential function. And in fact one way of defining the exponential function is as the solution of a differential equation like this. So what is the solution of this equation? In fact I have to be careful, I should not say the solution, because this differential equation dx dt plus a0x equal to 0 has not one but infinitely many solutions. So I cannot talk about the solution unless I am able to select or specify one of them. That is why one talks about not the solution but the general solution of this differential equation. By that one means the whole set of solutions. Fortunately, all the solutions can be described by one single formula. And what is that formula? All of you must know it. If not, then you have to go back to your first year and read up about it. No electrical engineer can afford not to know about this function and about some other functions. These are sort of bread and butter in whichever branch of electrical engineering you pursue. So what is the general solution of this differential equation? As you know, it involves the exponential function, and so the solution can be written as x of t, the solution at any time t, a particular solution among that class of solutions is given by x of t equal to some coefficient or some number k multiplied by x. This x stands for the exponential function, x of what? What is the argument of the exponential function? Now this is where one can make mistake. In order to avoid the mistake, I will write the equation as dx dt equals minus a0x. When that is done, perhaps one cannot make a mistake, and therefore the solution x of t will be k into exponential of minus a0 into t, or writing it in a different notation, using a different notation, k into e raised to minus a0 t. This gives you the general solution, in the sense for any number k it gives you a solution, and all solutions look like this. Choose k equal to 1, I will get one solution, e raised to minus a0 t. Choose k equal to 10, I will get another solution. Choose k equal to minus 10,000, I will get a third solution. All of them satisfy the differential equation dx dt equal to minus a0x, or equally well the original differential equation dx dt plus a0x equal to 0. And so that is why this is said to be the general solution, and by that we mean this gives you the set of all solutions. And to use a slightly better notation, I will put it like this: k x minus a0 t, where k is any real number. This set is the set of all solutions of the differential equation. As I said, we can take this as a definition of the exponential function, or alternately, if the exponential function is defined in some other way, which is what is normally done, then one can prove that this is a solution, and some more theory is required to show that these are all the solutions, there is nothing else. There are no other functions in the world which satisfy the differential equation. So then one can call this the complete solution, or the complete class of solutions of the differential equation. Now, when I have a particular system which is governed by this differential equation, of course I expect the system to behave in a particular way. So one of these is the solution that is applicable, that is, one of these will describe what is going to happen. So how do you get that? How do you get that particular behavior of the system? And this is where the initial value comes in. For example, if you not only know that the differential equation is satisfied, but you also know that x0 is equal to 3, that is, you know the initial value of the response or the output, then from this class of solutions there is only one that will meet this condition. This therefore is sometimes known as a boundary condition. Again, the term is a more general one from physics. In this case it is only an initial condition, initial meaning at time t equal to 0. This initial condition then tells you which of these is the correct solution and what is you expect to find, namely 3 into exponential of a minus a0 t. So the linear first order differential equation with constant coefficient which is homogeneous, its solution, the general solution, consists of multiples of an exponential function, and the particular solution for a particular system under particular conditions will be determined by the boundary condition or the initial condition of the system, namely the value of x at the time 0 that we have chosen as the initial time. We are going to look at the system from that time onwards. We are not worried about what may have happened in the past. The control theory person usually looks forward to the future because he wants things to happen in a certain way in future. Not to say that past is not important, the study of the past, what happened during the lab, what happened during earlier runs of the system, all that is of course useful, but we are faced with the problem of what to do from this moment onward to make certain things happen. So that is the idea of this initial time or the initial condition. So this is the solution of the simplest case. You should all be familiar with the graph of this function, what it looks like. Let me just draw it very quickly. Such graphs as I said, and such functions are the bread and butter of electrical engineering, and so one should be able to draw them with a proper shape. Being engineers, we cannot be very sloppy. Our drawings, as far as possible, should be neat and nice. Wherever possible, one should use a scale to draw a straight line. One should use a pair of compasses to draw a circle. I am not doing it here because if I do that, it will require much more time. But I hope my straight lines do look reasonably like straight lines. Anyway, my exponential function will look reasonably like an exponential function, and yours also must look like exponential functions. Now, these are not details which we can discuss in this course, but they are very essential. So, revise your graph techniques, graphs of elementary functions, how to draw them reasonably accurately and things like that. For example, if I want to draw the graph of just exponential of minus a0t, what will it look like? Well, one thing is certain, at t equal to 0, and this is my t axis shown as symbol t there, this is t equal to 0 if you wish, or just 0. The value of the exponential function at t equal to 0 is just 1, so this is 1.0. Everybody must know that the exponential function, when the argument is 0, x0 is 1, e raised to 0 is 1. What next? What will be the graph of this function for t greater than 0? Don't rush to an answer, because that depends on the number a0. If the number a0 is a positive number, as it is in many cases, if the number a0 is positive, then what's the function going to look like? As one says, the function is going to decay, it's going to decrease continuously. In fact, such a decay is known as an exponential decay for this reason, because the exponential function, for the reason that the exponential function turns up in many places. So what does the graph look like? Does it look like this? No. Does it look like this? No. So what does it look like? It looks like something which goes on decreasing continuously but does not become 0. So if you draw a graph where it shows crossing the t-axis, I will send you back to first year or even perhaps to your 11th and 12th standard. No electrical engineer can draw a graph like this and say that this is a graph of exponential of say minus 3t. No, simply not allowed. Go back and redo your earlier work. So it can't be like that. Also, it cannot have any shape of this kind. It cannot have this kind of an oscillatory behavior. It must have a behavior which is continuously decreasing, but the rate of decrease also goes on reducing in absolute magnitude. So it is something like this. Don't show it as intersecting the t-axis, but don't also show it very far away from the t-axis. Of course, I cannot draw the whole graph, because t equal to 10 seconds, 100 seconds, 1 million seconds, I will need a very, very long graph paper, and tends to infinity cannot be accommodated anyway. But this is what the rough shape should be like. And associated with this is something called time constant, and that is something you must also be aware of. Associated with a decaying exponential like e raised to minus 3t, let us say, is a time constant. So if the function is x minus 3t or e raised to minus 3t, what is the time constant and what is the meaning of the term time constant? It is not enough to know that this is the time constant. You must also know why it is called the time constant. What is the time constant for exponential of minus 3t or e raised to minus 3t? Is it 3? No. What is it? It is 1 by 3. Alright, it is 1 by 3. But why is it 1 by 3 and why is it called a time constant? One reason, and in fact the main reason for using this expression time constant and talking about it is the following. Look at the graph of the exponential function. It starts decreasing from the value 1.0. So the tangent is downwards, but the tangent becomes more and more horizontal as time proceeds. That is, the rate of change of the function goes on decreasing in absolute value. The slope is of course negative, but the absolute value of the rate of change goes on decreasing as time passes. So the slope of the tangent goes on decreasing in absolute value. But if you draw the tangent to this curve at t equal to 0, then that tangent, if this is the tangent, intersects the t axis at a point which therefore can be interpreted as the time, and this time is the time constant. And that is why the time constant can be then defined as follows. It is that time at the end of which the function would have become 0 if it had decreased at its initial rate of decrease. Initially it was decreasing at a certain rate, initially the tangent had a particular slope. If that slope, instead of changing, had remained constant, at what time it would have become 0? Well, at this time called the time constant. So look at this function, think of it as, say, y of t or x of t equal to e raised to minus 3t. Look at its derivative, which gives you the slope of the tangent. Then write down some appropriate equations and verify that at 1/3 of a second, if the unit of time here t is in seconds, then at 1/3 second this tangent would intersect, at that point this tangent would intersect the t axis. This is one interpretation of the time constant. That is, if the initial rate of decrease had remained constant, the function would be 0 at the end of the time duration equal to the time constant, in this case 1/3 of a second. But there is something else that also one can interpret, and that is what the exponential function e raised to minus 3t is not 0 when t equal to 1/3. In fact, I told you that this exponential function is such that it never becomes 0. Of course, practically speaking, this function may be so close to 0 that practically you may consider that the motor is off, the current is 0 and go away. That's a different thing. But the mathematical function, exponential function, never becomes 0. The function that we are looking at, such as e raised to minus 3t with exponent which is negative, that is minus a0, a0 is positive, so minus a0 is negative, such a function never becomes actually equal to 0. It only tends to 0 as a limit as t tends to infinity. Therefore, at 1/3 second after the initial time, the function will not be 0, but it will be what? E raised to minus 3 into 1/3, or it will be e raised to minus 1. So how much is e raised to minus 1? E is what? E is some 2.7 something, at least that one should know roughly. And so e raised to minus 1 by e, look at your calculator and find out what e raised to minus 1 is, up to maybe 2 or 3 places of decimals. It will be something like, say, 0.37 perhaps. Check. So at the end of one time constant, that is after a duration of one time constant, the function would have become about 0.37, or it would have become about 37% of its initial value. Initial value in this case is 1. So the time constant is also happens to be the time at the end of which the function becomes about 37% of its initial value. But the basic interpretation of the time constant is not this, but it is that rate of change at t equal to 0, the slope, the initial rate of decrease, and the fact that that tangent intersects the t axis at time constant. So if you want to remember this using this idea, then e raised to minus 3t, to find out what the time constant is, think of it as e raised to minus t divided by 1/3. So when t equals 1/3, this becomes e raised to minus 1, or 37%. So the time constant is 1/3 seconds and not 3. Many students commit this mistake: exponential minus 3t, time constant is 3. No, you ask them what is the significance, what is the meaning, why do you want to consider this at all, why do you call it time constant, they have forgotten. Don't forget it, it's very important, because a lot of control theory work is based on this concept of time constant, something happening within one time constant or within two time constants and so on. As an exercise, find out what will be the value of the exponential function e raised to minus 3t after a time interval equal to 5 time constants has elapsed, that is for t equal to 5 times 1 by 3. What will it be? It will be e raised to minus 5. E raised to minus 5 is 1 divided by e raised to 5. So, what sort of a number is it? Well, it will be quite a small number. Just find out what it is. Is it about 0.01 or thereabouts? Calculate it and find out. So, at the end of 5 time constants, then the function will become about 1% of its original value if e raised to minus 5 is approximately 0.01. It's not necessary to remember these numbers to any number of decimal places, but one must at the same time know them roughly. One must know that the number e is something like 2.7 something something, or the number 1 by e is roughly 0.37 or 0.36, a third place of decimal or whatnot. Or 5 time constants make the function nearly become 1% or less than 1% of its initial value, and therefore it's almost 0. Well, if not, wait for 5 more time constants, then look at e raised to minus 10, find out from your calculator what e raised to minus 10 is, and then you will get the answer as to what this e raised to minus 10 is. Is there a quick way of finding out what is e raised to minus 10? Rough idea? Is it 10 raised to minus 2, 10 raised to minus 3, 10 raised to minus 10? How much is it? Yes, again something which one can remember without too much difficulty is the logarithm of e to the base 10. What is the logarithm of e to the base 10? It's not a very difficult number to remember. If I remember it correctly, it is 0.4343. It is 0.4343. So what is the logarithm of e raised to minus 10? It is minus 10 times that, therefore it is minus 4.343. That is the logarithm of e raised to minus 10 to the base 10. So what is the number whose logarithm is minus 4.343? So first convert it into the appropriate form, therefore I will have to write it as 5 with a bar, this is the mantissa, multiplied by 6, 5, 7. So it is the antilog of 0.657 multiplied by 10 raised to minus 5. Now what is the antilog of 0.657? What is the logarithm of 2 to the base 10? Now this is a number which we will come across later, and again control theory people ought to remember that much. Logarithm of 2 to the base 10 is, look up your calculator, up to 3 places of decimals or even 4 places of decimals, 3010 or certainly 0.301, up to 3 places of decimals, 0.301, logarithm of 2 to the base 10. This will come across later on. It has something to do with what is called 3 dB per octave. This is something we will come across later on, and that 3 dB per octave is related to this 0.3010. It's almost 0.3, not quite, but almost 0.3. So what will be the logarithm of 4 to the base 10? 4 is 2 squared, so logarithm of 4 to the base 10 will be double of this, so that will be 0.6020. That will be the logarithm of 4 to the base 10. Now what I have is the number whose log is 0.657, so it is greater than 4. What is the logarithm of 5 to the base 10? Well, it is the complement of the logarithm of 2 to the base 10, because 5 into 2 is 10, so it will be 0.699. almost 0.7. Our number is 0.657, so it's a number that lies between 4 and 5 multiplied by 10 raised to minus 5. So e raised to minus 10 is about something, say 4 point some 1 or 2 digits multiplied by 10 to the minus 5. Now if the initial voltage was 100 volts, then it will be 100 volts into 10 raised to 5, so it will be about 1 millivolt. And therefore it may be considered as virtually 0 or negligible. So in that sense, after 10 time constants, the function would have nearly become 0. Nearly, not exactly equal to 0. The exponential function does not become 0 for any time t. I am saying all this because the exponential function is extremely important in control theory work. The sinusoidal function also will come across soon, and these basic functions, one must know them very well. You cannot do good control theory unless you have some idea of what these functions are as functions of time, what their graphs look like, and so on. So going back then, for the first order differential equation, the solution is an exponential function, and the solution will be determined by the initial condition, and it will be therefore some multiple of an exponential function with a particular exponent. If the exponent is positive, for example, if a0 is negative, then the behavior of the exponential function is quite different. And what is that called as? Instead of exponential decay, one talks about it as exponential growth. Now these are two terms which one must not simply use, one must understand what they mean, and one must be able to draw the correct graphs for these functions. So what does exponential growth look like? Again, let us say we plot this time e raised to 3t instead of e raised to minus 3t. Now once again, a mistake where in place of e raised to minus 3t you write e raised to 3t is not acceptable. The two functions are drastically different. If I get e raised to 3t in my control theory work, then I will be very, very suspicious and unhappy. But if I see e raised to minus 3t, that is no problem. So this function x3t or e raised to 3t, what will the graph look like? At t equal to 0, it has the same value 1.0, there is no problem. But now as t increases, the function keeps on increasing. The exponentially decaying function kept on decreasing but never became 0. The exponentially increasing function keeps on increasing, and its rate of increase keeps on going up. So the graph, the slope of the tangent becomes steeper and steeper. And what is the limit of it as t tends to infinity? It is infinity. That is, this function can become as large as you wish if you wait for sufficient time. Instead of e raised to minus 10, you can look at e raised to 10, and what will that be? E raised to 10 will be 10 raised to 4.3 something. So it will be of the order of 10 raised to 4, a multiple of 10 raised to 4, greater than 10 raised to 4. So e raised to 10 will be about 10,000. So at the end of 10 time constants, the function would have a value which is about 10,000. If the initial value was 1 volt, then the value at the end of 10 seconds or 10 time constants, 10 in this case, 10 time constants will be, the time constant is just 1, it will be 10,000 volts, and that just may not be possible. The system will have blown up, a fuse would have blown somewhere. So this is the exponential growth, and the other one was the exponential decay. With the exponential growth, there is no such initial slope kind of thing conveniently defined. So the time constant idea comes basically from exponential decay, but it can also be applied to exponential growth. That is, the same coefficient plays a role in the rate of growth as it plays in the rate of decay when the coefficient is negative instead of positive. So the solution of the first order LDEWCC homogeneous is an exponential function multiplied by an arbitrary coefficient. That is the general solution. What happens in the particular problem depends on the initial condition of that problem, and if we know the initial value, then that is that multiplying coefficient. So the first order differential equation was very easy to solve once you know what the exponential function is, and then you are able to actually show that the exponential function satisfies the first order differential equation, and in mathematics it is shown that it is the only solution of that equation. Now we can go on to the second order differential equation. So what will be the second order LDE Once again, why is it going to be called second order? Because the second order derivative will appear in it. We are still going to look at linear, because of that there will be something more, and with constant coefficient. So the second order LDEWCC will look like d square x dt square now, or the second derivative of x plus a1 dx dt plus a0 x. If it's homogeneous, on the left hand side I will have 0, on the right hand side I will have 0. If it's not homogeneous, if it has an input or a forcing function, then it will be that function u, which is our generic symbol or a standard symbol for an input. So this will be the second order differential equation. Now you will see why I wrote that coefficient as a0 first, and now I am writing two coefficients a0 and a1. a1 multiplies the first derivative, a0 multiplies the function itself, or if you wish I can call it the zeroth derivative, and the second order derivative is multiplied by just 1, therefore I do not write it. If it was multiplied by some number, I would have divided the equation by that number and therefore made that coefficient 1. So this is the second order LDEWCC. Now how to solve this? As I said, you know it, so we will look at it very quickly. But before we do that, a slightly different way of writing this equation, which we have used earlier, I will use it again because it is very convenient and compact. We will denote this operation of differentiation by the symbol capital D. So capital D will stand for the operation of taking the derivative of anything. Therefore, we will rewrite this equation as d square x, and I am saying d square, although I do not really by that I mean some number squared, but d applied twice. Take x, apply the operation d to it, that is take its derivative, and apply the operation d again, that is take the derivative of that derivative. That is exactly what d square x dt square is. So d square x plus a1 times dx, dx is simply the derivative of x, plus a0 times x equal to either 0 or the input u. We will see why it is advantageous to write it in this form. Okay.